A master's degree in physics at the University of Nottingham in 2003. When he graduated, he moved to the University of York to study for a PhD in the Department of Computer Science. And most of his work has involved the exploitation of the polarizing properties of reflection from surfaces. In 2007, Gary moved to University of West of England and to the Centre for Machine Vision, and that's now part of the Bristol Robotics Laboratory. And he's since researched a range of areas in computer vision, including 3D image analysis of plagiocephaly, which I hope, Gary, you're going to explain to us what that is, industrial inspection, reflectance analysis, and security and CCTV imaging. So without further ado, I'd like to welcome Gary and pass over to Gary to give his presentation. Thanks very much, Gary.
Okay, thanks, Alan, for that introduction. The first two things I'll say, plagiocephaly is actually the cranial deformation of children's heads during the early years of life. But I won't be talking about that actually, because that's not quite within the remit of this presentation.
Okay.
The second thing I'll say is I've been a little bit unwell, I'm afraid, this last few days. Feeling a little bit better now, but just so you know, if my voice starts to collapse halfway through, I might just take a moment just to give you a warning.
Yeah.
Anyway, let's get on with it. So thanks for that. So as Alan said, I'm going to talk about machine vision and this quite a niche application in a way. But what I plan to do today is divide this talk into three parts. Okay, the first part is very general, and that is about the field of computer vision at large in industry, in particular manufacturing. And I've included that part mostly because I've got quite a broad audience, I understand here. So apologies if you're already an expert in computer vision, but for those of you that are not experts, hopefully that will be a useful overview for you. And if you are already an expert, then maybe it'll be interesting just to compare my take on the current state of the art compared to yours. I then want to talk about my primary area of expertise, which is the field of polarization, both in a physics sense and in terms of polarization visions, it's come to be known, which is a small subfield within computer vision. And then the third and final part is where I'll actually apply these theories and these methods to carbon fiber composite surfaces. So that's the outline for the next 45 minutes or so. So I'll spend about 15 minutes on each. So first of all, I borrowed a couple of slides from my undergraduate teaching material just to kick us off, just in case you're not familiar. So computer vision, my interpretation of the field is that it's the opposite of computer graphics in a way. Because if you think about computer graphics, you're trying to generate an image of a surface, and you're effectively taking some information about that surface and then using that to generate an image or a video of it. So for example, if you wanted to generate this image of a wooden box, you would need to know the shape of the box, like for example, the coordinates of each vertex. You'd need to know the material. In this case, it's a wooden surface, but not just that it's wooden, but the type of wood and everything. You need to know something called the BRDF, which is a bit of a mouthful. It stands for the bidirectional reflectance distribution function, which basically tells us about how the surface reflects light. Okay, because a piece of paper compared to a painted surface, a white paper versus white paint, and they're both obviously the same color, but they might reflect light in very different ways. Like, I mean, paper, for example, is very diffuse, matte, whereas paint might be glossy. So that's encapsulated in the BRDF. And finally, you need to know about the lighting directions. And you put all that together and you generate this image. So in computer vision, it's doing the opposite, basically. We're taking an image and we're trying to extract some useful information from that. Now, admittedly, the image, it won't be a synthetic image. Obviously, it will be a real image, So for example, it might be an image of a component, and the information that you extract from that might be the geometry of the component, and then you might compare that to some specified tolerance. But it's effectively doing the opposite of computer graphics. Now, we often hear the term machine vision as well. Often people use the terms machine vision, computer vision interchangeably. I often do that myself, to be honest. But I think machine vision tends to be a more industrial application. So for example, probably what the audience here is most interested in, industrial inspection, applications of Industry 4.0, that sort of thing. Whereas computer vision, it includes that, but it will also be sort of commercial sector and computer games and things like that. Now, as you can see, again, this was just second and final slide taken from my undergraduate teaching notes. You can see there's lots of applications of computer vision in all these different areas. The industrial applications, actually, perhaps some of the first applications, but it's become prevalent in medicine and in security and other areas as well. And since Microsoft released their first Kinect sensor, it's been used in computer games, that sort of thing. Google love it, of course, with their Street View, as you can imagine. But we want to focus, I guess, mostly on industry here. So this is a piece of software called Vision Builder, which is made by National Instruments. And I use this for some basic tasks in computer vision, because this shows you the power, in a way, of computer vision for people who have not seen it before. So Vision Builder is just like a development environment that allows you to piece together well-established methods of image processing and computer vision to extract information that you might need about a component in industry. So this is a rib component from an aircraft wing, and you can see it's found that various holes on it, and it's been able to identify this angle here and other things like that. And it took me about 15-20 minutes, maybe 20-25 minutes, let's say, to put this script together, because these well-established techniques can be applied very well to many industrial applications. And one of the things that we've got in our favor when we work on industrial projects, and some of you might disagree with me depending on your exact roles, but generally speaking, we've got quite a lot of control over the environment in manufacturing plants, for example. Whereas when you move to application areas, for example, out into the entertainment or driverless cars, we don't have that control over the environment. So the techniques you need to use would be a bit more sophisticated. Now, you might be surprised that I want to talk about history, but it's quite useful to do this at this stage, because we are at a very pivotal moment, I think, in the field of computer vision. And you'll see why if we just look very, very briefly at the history, because it's kind of been around maybe since the middle of the century, 20th century, when people first started to digitize images, really. People already started to process images and try and get useful information from them. But it was, I guess, the 1970s was when it became a discipline in its own right, and people started to use it for sort of preliminary or rudimentary attempts at inspection or tracking particles from a accelerator chamber, that sort of thing. And then in the 1980s, some would argue that was the coming of age of the field, when many of the classical algorithms had been formalized. Other people would argue that progress was quite slow during this time, because although the algorithms had become established, we didn't really have the imaging technology or the computational capacity to do all that much with it. But I think a few people would argue against the 1990s being the decade where it really did become firmly established, and most, or at least many, academic institutions had their own computer vision group within engineering or computer science, and first companies started popping up. And what's interesting, the reason perhaps why I want to tell you about this now, as I reflect on the state of the art, is that a lot of the methods that we use today, for example, all of the methods from this demonstration here, were pretty much established by the early 90s. And we still use a lot of those techniques today. And you often hear about research in the field talking about how amazing their neural networks are and things like that. And they are, and we'll talk about that in a minute. But it's important we don't forget about these existing techniques, especially in the industrial sector. But nevertheless, we shouldn't ignore latest developments. Artificial neural networks, they've been around for almost as long as, or maybe as long, in fact, actually, as computer vision. But it was from the 2000s where a type of neural network called convolutional neural network started to transform things. And this is not meant to be a primer on CNNs, but suffice to say that CNN technology these days applied to, for example, image classification, handwriting recognition, that sort of thing, can actually supersede a human capabilities to categorize these types of images in not all areas, of course, but in some areas. But that doesn't mean that we need to override what we've already achieved over the previous decades. And I think this is quite a pivotal time because we've got the firmly established classical methods of computer vision, and we've got the state-of-the-art CNN technologies. And what we're finding now when we're applying these techniques to industrial applications is it's a bit of a mishmash between very basic methods that have been around for 30 years and then these super high speed, so memory intensive, computational intensive CNNs. So we've got a bit of a convergence of very old versus very new methods. So I think it's really, quite a remarkable time really for the field. And one thing that actually strikes me is that the term computer vision is not really a household name and a household term yet. If you go to your average person on the street, maybe 1 in 10 will say computer vision, never heard of it. And yet it's so prevalent in our day-to-day lives, we don't even know about it. Anyway, that's a bit philosophical there. Let's get back on track. So computer vision at the minute, that's where we're at. We've got lots of traditional methods, well established, got the development of all these CNNs and machine learning methods. But the other big development of late, which I think is perhaps a little bit overlooked, relates to the sensing technology. And I've just realized I'll come back to that point in a minute. So when you think about how we might want to apply computer vision algorithm to a particular problem, it's only natural that we draw on our human experience. So our human eyes, they're sensitive to the intensity of light. So it's not surprising that standard cameras, whether it's a monochrome camera or a color RGB camera, it's not surprising that those have dominated the field of computer vision for a long time. We're also sensitive in a way to depth information. Obviously, as we walk around the world, we see the world in 3 dimensions. So it was quite a logical step for us to include depth information. That's the D in RGBD. So that's why these sort of modalities have dominated the field so far. But one thing I'm particularly interested in is one of the latest developments, and that is to use things that are not obvious to the human brain, as I just check the time, okay. And the human eye. So one thing is infrared, or to a lesser degree, ultraviolet sensitive cameras. And obviously our eyes are only sensitive to a small fraction of the electromagnetic spectrum. So we can use infrared, thermal or near infrared, depending on the applications. That's one thing that's not new, but that's one thing that's not perhaps quite so obvious, but it's well established. What's not so obvious though are things like multi or hyperspectral cameras. So these are cameras where you don't just get an intensity, for example, this much blue light, this much green, this much red. In a hyperspectral camera, you'll get the full spectral response of a particular surface at your fingertips. It's not obvious that would be useful because our eyes aren't sensitive to it, but it is useful, and it's finding more and more applications. So for example, it's useful for sorting different types of plastics for recycling because they have different reflective properties in different wavebands. And also, I'm working on a project right now, in fact, that's being used to assess the quality of tomato crops. That's something that's becoming, well, that is quite novel in itself, but within the area of agricultural technology, hyperspectral cameras are being very, very useful to monitor crops. And obviously we want, with ever increasing world population, that's a central problem to the world's food crisis. And then it leads on to the bit that I find myself in mostly, and that's the polarization of light. Okay, our eyes aren't sensitive to polarization of light, and so again, it's not an obvious thing that we would draw upon to do some inspection or other work. But that's not to say that it's not useful. And in fact, there are a few animals that are sensitive, mostly marine animals. Also a few insects that make use of polarization patterns in the air or in the seawater. So we drew a little bit of inspiration from that, but mostly it's not necessarily inspired by nature. It's just something that computer vision hadn't really tapped into. So we pose the question, can we get something useful out of it? And that leads me on to the second part of the talk, which is about polarization and polarization vision. So just in case you need a reminder from your school physics days, maybe some of you have got physics degrees, so apologies if that's the case, but light is essentially an electromagnetic wave. That is, it's comprised of an electric field component and a magnetic field component, oscillating perpendicular to the direction of propagation, as shown in this diagram here. Just to simplify things a little bit though for today, let's just consider the electric field component. Now, most natural light and the majority of artificial light is unpolarized. If you were to do a thought experiment and imagine here some light beam moving to the right, and then you're looking against the direction of the light, and then if somehow your eye could tell you what direction the electric field was in, excuse me, it would continually be changing its direction, and you'll see that it would be equally spread in all directions, perpendicular to the direction of travel. That's sort of in nature. Now we can of course change that by passing the light through a Polaroid filter, for example, the sort of thing you get in some sunglasses. And if you did that, so basically a piece of glass with lots of fine conductors all aligned, what happens is it will only allow the components of the light with the electric field aligned with the fibers to pass through. So you get what we say is completely linearly polarized. Okay, we say linearly to distinguish from circular polarization, but we won't worry too much about that for now. The important thing is that it's completely polarized. Well, give or take. I mean, in practice, it'll be a bit less than completely. Now, the other thing is, this is why I'm interested in this. Okay, that's just a bit of background physics. But when light is reflected from a surface or scattered in the atmosphere, it will also become partially polarized. Okay, so in this case, we can represent that using this diagram here. So the red wave, or the big wave, this is the component of the electric field that is the maximum value. And then at 90 degrees to that, we have a component which is the minimum value. Okay, so this is a partially linearly polarized case. And my aims over the last years has been to exploit this phenomenon, the fact that when light is reflected from a surface, it will become partially polarized. How can we measure that, and what information can we garner from that about the surface? Well, to do that, we need somehow to parameterize the state of polarization. Now, if you look in the physics or optics textbooks, you'll probably find things like the Stokes vectors. But in computer vision, we use something that's a little bit more easy to get your head around. And physicists like to sort of make life awkward for people. Okay, so we're trying to, and then more engineering, we're trying to make it something that we can get our heads around a bit easier. So we have three properties of the light. One is the intensity, which is not really about the polarization. This is just the overall intensity of the light. Then we have the phase, also known as the angle of linear polarization. So for example, that would be given by this angle here. So relative to some reference angle, what is the orientation of the maximum electric field direction? So we'll call that phi. There's not much maths in here, by the way, don't worry. It's just a bit easier to explain a little bit. And then finally, we have the degree of polarization. So this is the ratio of the polarized to the unpolarized light. So for example, if the degree of polarization was 0, it means unpolarized. If the degree of polarization is 1 or 100%, it means it's fully polarized. And then it can take anywhere in between. So this one, for example, might be 50% polarized. So that's how we're going to parameterize the state of the light. Now, let me show you a real polarization image now. So that is an image built up of these 3 components. Okay. So on the left, we have the intensity image. So this is actually an image of a snooker ball, which is quite timely with the World Championships underway. That is just standard grayscale image, remember. Okay, so you know what it looks like. This middle image is the phase image. I'll tell you how I calculated this in a minute, but let me just show you the result first. So the phase image, remember, that is encoding this angle here. Yeah. So you can see straight away that the phase is somehow aligning itself with the surface orientation or the surface normal. So that sounds like it's going to be quite useful to do some surface analysis. And then the degree of polarization, you can see, is also somehow related to the surface angle because it's getting very high near the edges of this sphere. So again, it's giving us some information about the surface orientation. So that's just to show you that we can get something useful out of it. I'm not just doing this because I'm interested in physics. Now, let me just check time a second. Okay, so I won't go perhaps too much onto this slide. This is just a little animation that I put together for a conference one time. Just to illustrate the point that if you imagine a piece of light or ray of light impinging on a surface like that, so we'll just pause it, for example, here. So this is like a classic textbook example. Here's the incoming light. As we know, some of that light will get reflected. But this red line here, so this red line here, this tells us the amplitude of the electric field in the plane of reflectance. So you can see that depending on the angle, if we go to this angle here, we can see there's a big difference between the two. Which means that, and then here it's a small difference. And the fact that these are different tells us that the amount of polarization that we measure in this reflected wave, reflected ray, must somehow relate to the orientation of the surface at that point. And this graph at the bottom is to point that in a graphical term. So you can see that as the angle of incidence increases from 0 to 90, we get up and up and up, and then we get a drop off near the end. Okay, that's well-established physics. A bit more recent bit of physics, though, is to consider this for more complicated surfaces, because that is just assuming that the surface is a mirror. Now, it's not very useful to engineering community just to have a method that only works with a mirror. So what we've done, well, not me, but other people have done this bit. They've built up these sort of physics-based models about what happens when light is internally scattered beneath or close to the surface of the material, and able to predict, in this graph here on the bottom right, that the degree of polarization still relates to the angle of incidence, but in just a different manner, like that. Yeah. So it's showing us again that if we can somehow measure this degree of polarization, then we can work out what the angle of the surface is. So for example, to do inspection or robotics things. So how do we measure that then? Yeah, because sorry, I should say as well that also that is why these images look the way they do, because the surface is related so closely to the polarization state of the light. Obviously, I've glossed over some of the finer details. You can read about that in the paper, the various papers. But we need to measure it. So how do we measure this information? Well, the most established way to measure this information is to take a standard camera, put a linear filter in front of it, and then image the surface as you're rotating the filter. And then each pixel on the image what you should find is that the intensity varies as a sinusoid like this. Okay, so if you measure the intensity at various polarizer angles, then you can fit the data to a sine wave and fit it to this is the equation here, sine wave, and from that sine wave you can extract the phase angle, the angle of linear polarization. You can extract the intensity, which is this bit of the equation here, and you can also extract the degree of polarization, which is just the ratio of this bit to this bit. Okay. And that allows you to build up an image of the polarization state at each point. And I've built this camera that does that. And it's quite accurate, but the problem with it is obviously it's quite time consuming, because even though in this case I've motorized the filter, controlled it with an Arduino and a stepper motor, it still takes quite a long time. So you wouldn't be able to use this for many applications, and for the moving surface, for example. So the second approach, which Sony, who of course got a lot more money than I have, were able to develop, as well as a few other people like some colleagues at Fraunhofer Institute. They've built cameras that are able to capture all of the information very, very quickly. And the way they do that is they take a standard sort of CMOS sensing chip, and they put on it at each pixel level a very, very tiny microfiber polarizing grid. Okay, and each pixel will have a different orientation of the grid. This is the pattern you can see. So we break the image down into these units. So each unit will have one pixel with vertical polarization passing through. One pixel will have a 45 degrees, one at 90, and one at 135, and so on. And then a few simple equations can then be applied once you've captured the entire image like that, to determine the polarization state at each point. Okay, simple linear equations. And then and that will allow you to calculate the intensity, the phase or the angle, and the degree of polarization. And although that's like limited by the resolution of the camera, it does mean that you can do that very, very quickly. I think Sony's camera, for example, operates at standard 25 frames per second. Don't quote me on the exact figure, but it's that sort of ballpark. 4 megapixel camera. So the resolution is mostly limited by what lens you've got on the camera. But that's the useful thing about the camera, is that the sensor is a standard CMOS sensor. The clever bit is the filters and these like lenses on top of the filters that give you the polarization state to each pixel. So what have we done with this sort of thing? Well, as you can see, we've animated a cat. So this is the first work I did in the field. So I took, in this case, it was my manual camera like that, standard camera with a linear filter on it. And I captured the information at each point. I applied a method from elsewhere in the computer vision literature to convert from all of my individual measurements of surface orientations from polarization into a 3D depth map. And these are some of the results I got. And on one hand, I was quite pleased with these results because it's quite an efficient way to capture the data. And well, I mean, you can see that they're quite promising results at first sight. And at the time I did this was actually for my PhD. So this is like in the late noughties, if you like. The competing technology for 3D capture at high speed was binocular stereo, which didn't have very good performance against smooth featureless surfaces like this. And now, unfortunately, however, more recently, other technologies have been developed that are faster than this and more accurate than this. For example, projected pattern imaging. In fact, I'll show you an image later from a company called GOM, which are very quickly able to capture this sort of data much, much more accurately. So they didn't really have that niche area. But the thing with polarization is it's tapping into a phenomenon that we don't normally know much about. That's what I said quite a long time ago with hyperspectral imaging, polarization imaging. It's not doing such obvious things, so we can use it in less obvious applications. So, for example, somebody I know who works at the, well, I know, met him a few times, who works in the University of Hiroshima in Japan. What he's done is applied this method to transparent surfaces. Now, as you can imagine, transparent surface is a nightmare surface to inspect because, well, you can see through it. But the good thing about using polarization information with a transparent surface is that the polarization state of light that's emerging from the surface is not necessarily affected by what's beneath it in the same way that the intensity is. So he developed this method with his colleagues to develop to construct a 3D map of this glass hot, for example. And more recently, a few inspection vision companies have tried to do similar things using polarization to inspect glass because it's such a difficult thing to do. But what I turned my attention to is another difficult surface, and that is carbon fiber. And as you might be able to tell, my voice, I think it can just manage for the third and final part, hopefully. Yeah, carbon fiber inspection. That's what I turned my attention to. So let me just check how we're doing for time. Okay, a little bit behind time, but we should be okay. So carbon fiber, as most of you probably know, consists of a sequence of carbon fibers aligned with each other and then set in some sort of resin, as shown in this diagram here that I've borrowed off paper in polymers. And a carbon fiber component usually consists of lots of layers like this, placed on top of each other at various orientations. And the main advantage, of course, is that it's got a very attractive strength to weight ratio. But the manufacturing process is quite complicated and quite expensive. And also it still involves a lot of manual layout processes. There's a lot of work towards automated tape layout and things like that, but still a lot of manual layout. And even the automated methods, as I've personally discovered through working at National Composite Centre here in Bristol, even the automated methods suffer because the raw materials often have defects in them. And the thing is with the carbon fiber component is that any defects can have a massive impact on the overall macroscopic properties of that component. So defects such as inclusions or broken fibers, gaps in the toe, voids, things like that. All of these can have quite drastic effects on the performance, but they're quite hard to find. Just as the transparent surfaces are hard to inspect either manually or using automated methods, so too are carbon fiber components because, well, they're black, for one thing, not the easiest thing to image.
Processing of features.
Also, is there some microphone on?
Might well be.
Yeah, so that they're black and they're shiny. Black shiny surfaces are, I guess, the worst possible case, maybe along with transparent surfaces, to do automated vision-based inspection on. So that's where we came in. So here's an intensity image. So this is a woven surface. So just in case you've not seen these before, instead of having the fibers layered on top of each other like this, you just literally weave them between each other before you embed in the resin. So here's an intensity image. You can see how difficult it would be to spot gaps in the fibers or broken fibers using this image. But what we did, and by we, I mean myself and colleagues in the BRL, and also colleagues that I went to work with at Fraunhofer Institute near Nuremberg, we imaged these surfaces using polarization camera. So this is using the one that Fraunhofer developed, which is very similar principles to the Sony version. And you can see the phase image, or the angle of polarization, is aligning itself with the fibers. Okay, and the reason for that is because the fibers are effectively, it's like forming an anisotropic conductive surface. Yeah, it's a bit like a reflective version of a pair of Polaroid sunglasses. They're only allowing a reflection at a point with a given polarization angle. So that gives us a very, very efficient means to extract the fiber angles, and therefore some of the defects. So for example, you might even be able to see here, it's not a big defect, but there's a few defects on the surface that would have been very, very difficult to pick out without this false color image that we've generated using the phase data. And you can also do things like plot that. I mean, this is just a demonstration of what you can do, really. It's not an industry standard yet or anything like that, but we just plotted a histogram showing the phase measurements. And you can see that we've got two peaks, as you'd expect. One peak corresponding to an angle close to horizontal, and one is close to vertical. And the difference between these two peaks should be about 90 degrees. And as you can see, it is. In case there's anybody in the audience who is incredibly astute, you might notice that actually the peak here is not 0. That's just because I've just shifted them across a little bit to make it a little bit easier to see. The raw histogram was close to 0. Now that's good because it's a global measure of the quality of this woven composite surface that you can extract and calculate in less than a second, actually, for that. So it's very efficient. If you wanted to localize the defects, it's a little bit more challenging. So here's a 3D surface as well, but I think it's a bit low on time, so I'll move on from that. If you wanted to localize the defects, you can do that as well. A little bit more challenging though, because the defects can take many different forms. Okay, what we've got here is some recent work that we've done with National Composite Centre. So on the top right hand side, you can see an intensity image, standard image of a unidirectional carbon fiber surface with a sequence of defects that we've manually induced. And you can see most of the surface is black because we've got a black surface, very difficult to work with. And you can find some of the defects, like fuzzy areas and things like that, but it's not very clear. However, if you then image the angle of polarization, you can see it's highlighting the defects a lot better. And also the degree of polarization is able to highlight the defects. And then what we're doing then is pretending that this is like an RGB image, and then we're showing it like that. That's why it appears green. There's not big significance of the fact that it appears green. It's just that's how it appears as we combine them. And then we've applied a CNN, because you can't do too much work in computer vision these days without applying a CNN. Now CNN is a machine learning method that we were able to train using a bank of manually induced defects. And as you can see, it's already been quite successful at highlighting these defects. Admittedly, these are fairly large defects, but we are in early stages of this research. The next steps is not just to detect the defects, but also to classify them. You can do that with the CNN, no problem, if you've got enough data. And of course, companies that do manufacturing with carbon fiber, first and foremost, they want to know if there's defects and where, but it's also useful to know what the type of defects are, because they won't be able to, if they want to improve their production line, they obviously need to know what type of defects they're getting. We're also applying a combination of techniques involving structured lighting. So this is a temporary rig that I've built to try and extract out of plane defects, because one of the limitations of polarization is that most of the work so far is only treating the surface as a plane. But this method that I'm working on at the moment is to look for out of plane defects. And also we're looking at this in repair, and actually we're working on a major proposal for this now about scarf-based repairs. And this is where you have a damage to a composite component, and then you scarf out either via, via grinding, or more recently via laser ablation methods. You grind out the damaged area, and then you need to repair it with a patch. But often you don't know what the underlying layup structure is, or how much material to remove and things like that. So we're looking to optimize that. So we're working on this right now. So if anybody is interested in working on us with us on a related area, or think you've got something to contribute, then feel free to give me a shout. Or Adrian Murphy is also working in this area. But that concludes my talk. So what I tried to do is give a bit of a general overview of computer vision for the industry, for those of you not seen it before, but also with a focus on the state of affairs and where we're moving. And then I wanted to move on to my field of polarization, and then how it can be used for carbon fiber and other challenging surfaces. Last two slides very briefly, just slightly going to abuse my position ever so slightly and use this opportunity. If anyone's got any work that they want to publish, I'm currently running a special issue on new applications of computer vision technology for Electronics Journal. So if anyone's doing something like this that they think is using computer vision in a new area, feel free to give me a shout on that, because I think that'll be a good match for this journal. And also, I just wanted to point out that the latest work we're doing is funded by DETI, which is a Southwest Partnership Program, which has been very successful at bringing ideas from industry and academia together via the NCC. So again, if you feel that you've got some ideas that relate industry to academia, like through the Valley of Death or something like that, then DETI is a good place to come. I'm not a big person within DETI. I'm just working on one of the projects, but give me a shout if you think that'll be useful, and I can put you through to the person that matters. Just about made it. Any questions, feel free to give me a shout either now, or you can drop me an email.
Thanks very much, Gary. That was extremely informative and helpful. If anybody has got a question, sometimes it's helpful to put it in the chat function, and we've got one already. So this is how, Dr. Vasquez, how quick is the identification of defects?
So I assume you're talking about these defects. I do apologize. For the last 5 minutes, my cat was scratching at the door. I let her in, and now she's meowing at me. This wouldn't have happened if we'd been able to meet in person. Yeah, how quickly? So if for anyone in the audience who doesn't know much about CNN technology, with CNN, you need to train the network, and then you need to run the network. To train the network requires lots and lots of data, and it could take several hours to train it. But once you've done it once, then you don't need to do it again. The actual detection process is not quite real time, but very, very fast. Yeah, less than a second to detect a defect.
I was fascinated, Gary, that you can, using your hyperspectral camera, you can identify and separate different plastics.
Yeah, that's not my own work, but because every plastic has its own absorption spectrum, which isn't, if you it's a bit like reflectance of the sun, like spectrographs and things. You, as long as you know if there's a difference between what wavelengths are reflected from one plastic compared to another, and you can measure that spectrum, then in theory, and in practice, it's proven, you can distinguish some plastics from other plastics. It's not something I've worked on myself, but last time I looked, I think one of the problems was that although it can distinguish many different types, it can't distinguish all types of plastic. And therefore you might have a few sort of unknowns and potentially contaminate a recycling batch. But yeah, it's not exactly my area, but you can definitely do that.
Yeah, Are there any parallels with Raman spectroscopy in that?
Well, I guess they are, because I mean they're both, again, moving off my area somewhat, but both of them are looking at absorption and reflectance of different wavelengths.
Yeah.
So, yeah, similar sort of principle. I think that the technology that it uses to obtain the images is different, but I think the underlying physics, I understand, is closely related.
Yeah. Oh, very interesting. Okay, there's a question from Adrian Murphy. How does the tolerance of measurement change with the different sensing technologies?
When you say the different sensing technologies, Adrian, you mean polarization versus non-polarization?
Yeah, is it simply the pixels? Is the pixel count per square inch the key parameter for both?
No, actually, obviously that matters, because you can't have, that you're limited by the resolution of the camera. If you've got a 10 by 10 pixel camera, then obviously you're limited by that. But it's highly limited by the lens, one thing, but also the type of surface. Okay, because some carbon fiber types, especially if you're looking at dry fibers, so dry fibers can get a little bit tangled up, and you can get interreflections between the various fibers, and that will limit your measurements precision. Well, what tends to happen is, if you've got for example, if you take this surface on the left here, obviously this is not a real surface. In this synthetic case, all of the fibers are perfectly aligned. Now, if you imaged that using polarization technology and you plotted the histogram, ideally you would get something a bit like, I'll just get my pen, it'll be flat, and then as soon as you get to the corresponding angle, you get a big sharp peak, like that. That's what you'd get in an idealized case. In practice, due to noise and other factors, you'll get, of course, a bit more of a normal distribution or something like that. But then also there can be a range of other factors. For example, if the lighting is not uniform, that might cause a bit of a skew, a bit like I've inadvertently included here, actually. So what we've been doing, we've been putting the fibers under a dome illuminator, so we can be certain that the surface is illuminated from all possible directions. So that's the optimum case. Having said that, you don't have to do that. It's just that's the optimum case. So it's affected a little bit by resolution, a little bit by the quality of the material, and a little bit by the illumination. But you can normally measure to about a degree precision.
Brilliant, thanks, Gary. I was just for maybe a quick one. So there's nothing in, if you had a microscope lens, there's no reason why this couldn't work at a very small scale, looking at small features.
No, not at all. In fact, I've already done that because I was interested in understanding this distribution, which is ongoing work, so I'm not able to answer that quite today. But yeah, you can absolutely do it under a microscope. And interestingly, you can also pick out any binding agent on the microscope, which has different reflective properties. And that actually is potentially one of the reasons why we that might limit the precision of this, is that if you've got a lot of binding agents, that might scatter the light somewhat. But all of these questions are current research questions.
Brilliant. Thanks, Gary.
Thanks, Gary. Now there's a question from Nawal Prinjar. These are all for surface stroke visible defects. Any ideas for hidden defects like lamination tears, etc.?
Yeah, so you're absolutely right. Polarization technology is very much a surface technology. So there's pretty much no way that I can think of that you could use this to look for subsurface defects. So if you wanted to do that, you would need to use things like ultrasound, like a CT scan. Having said that, one of the applications of this, though, is not necessarily as a post-manufacture inspection, because obviously, you, as you say, if you've got a void or delamination, then obviously that will be a major thing that you're missing if you don't detect something like that. So the idea is that we build this eventually into the production line, so that during the layout process, defects will be detected as they happen as part of the Industry 4.0 standard. But yeah, you certainly wouldn't be able to detect a defects 3 layers deep on a fully manufactured final part.
You've kind of answered Anil Pradhura's question, which is how deep below the surface can the defect be before it goes undetectable?
Yeah, the only thing I'd just add to that is the more recent work that I'm doing. Just briefly look at, what was it, this slide here. I mean, you can probably garner from the quality of the component. This is sort of a prototype, but certain close to but not surface defects will have a telltale sign at the surface, because, for example, if you've got a gap in fibers, then often that will manifest as either indentation or as a lump on the surface. So this is the sort of technology combined with polarization that will allow you possibly to detect a little bit beneath the surface, but it is very much relying on secondary effects. The truth is that, you know, computer vision is inherently a surface-based technology. There's only been a few attempts at subsurface inspection using standard computer vision. You really need, you know, infrared thermography or ultrasound to probe the surface.
Yeah. Another question from Nawal. Which AI model will you recommend if we use ultrasound? Will short-term memory, LSTM, work for ultrasound?
LSTM, well, that's the recursive network, isn't it? LSTM. I mean, ultrasound will give you, they've got an ultrasound technique. The output would be a 2-dimensional image, single channel, and presumably you would be able to have access to lots of defective parts using ultrasound, which you could manually label. So you'd probably use something like a RCNN, you know, Regions Convolutional Neural Network, or here we used YOLO architecture for localizing the defect. But the fact that you're talking about ultrasound data, if you have the image, it doesn't really matter too much that it's whether it's ultrasound or whether it's a standard intensity image or polarization image. I'd still probably use transfer learning using existing regression network. But if you're talking about LSTM, that might imply that you don't have an image. So probably need to know a little bit more about your particular application to answer that any more details.
Great, thank you. One thing that, by the way, that struck me, which you were saying that people aren't using the expression computer vision, and I suspect the reason is that for those of us of a certain age, computer vision is actually the American company that was dominant in CAD in the 70s, 80s, and 90s. So, you know, younger people like yourself probably don't associate the word with that company, but others do actually.
I have to say, no, I don't know that company, but I do know that my supervisor, a lot of the earlier researchers in computer vision, funny enough, like me, were from physics, not that I was one of the earliest, but yeah, my supervisor was an early adopter, and he went to Stanford and did computer vision. I think it was on the particle tracks from the linear accelerators for tracking that. So that was like one of the early applications.
Yeah, well, that company, the one called Computer Vision, was really dominant in the 80s and 90s for CAD software. And I think they had a deal with the American Navy worth hundreds of millions to provide CAD software. So, you know, some people automatically think CAD, you know, when they hear the word computer vision.
Well, I'll Google that as soon as the questions are finished.
Okay, well, I don't think there are any more questions, so we're coming up to one minute to 2 o'clock, so we're pretty much bang on time. And I'd like to thank you again, Gary. That was, as I said, it was very informative and really taught us a lot about this subject. If there are any questions, they can always be channeled through Pamela or directly to yourself. But this will be available on the network's website as a webinar. So it would be, it's quite likely that we'll get more questions as time progresses. So I'd like to finally thank you once again, Gary, for that. Really, really useful.
You're welcome. You're welcome.
Okay, so we'll leave it at that.